Welcome back to PV Online, and today we're going to take a look at how to solve problems if you have projectiles at an angle. What we need to do is we need to modify our equations to work for a projectile at an angle. And we're going to use our old kinematics equations, but we're going to make them specifically for what's happening in the horizontal direction and the vertical direction. So I have my horizontal components. I'm going to focus solely on what's happening horizontally and vertically. All right, so let's go ahead and go back to our kinematic equation for displacement. And remember, it was the initial velocity times time plus 1/2 at squared. Well, the horizontal displacement, we call that the range. That's a very specific displacement that we're looking for. So I'm going to substitute in where delta x is. I'm going to put in r for the horizontal range. Now for the initial velocity, I'm only interested in the initial velocity that's in the x direction. So if I have my initial velocity, we're going to have to find this component. And we do that using our trig function. So I'm going to need the initial velocity in the x direction, and later I'm going to need the initial velocity in the y direction. So I need the initial velocity in the x direction. And time is going to be the same whether it's horizontal and vertical. And remember, the acceleration is going to be 0 horizontally because the only force acting on it, or the only thing acting on it, is gravity, and gravity acts straight down. So from now on, when I'm focusing on what's happening in the horizontal, I'm just going to look at my range equation. Secondly, we've got the vertical. Now remember, we've done this before, so we're using our kinematic equation again. But what's going to be different this time is now all of a sudden, I'm going to use g for gravity. This time my initial velocity isn't 0. So when I do this, if I'm looking at the vertical displacement, it seems reasonable for me to use delta y instead of delta x. My initial velocity, I want the initial velocity that's in the y direction because I'm only focusing on the vertical here, times t plus 1/2 gt squared. Now when you did the problems with the horizontal launch, remember we were able to cancel that term out, and now we can't. So let's go ahead and take a look at this problem. We have a football is kicked with an initial velocity of 25 meters per second at an angle of 40 degrees. So over here we know this is 25 meters per second, and my angle is 40 degrees. I have to find out the component, and so for the horizontal component I need the adjacent side, which means this is going to be 25 cosine of 40. Relative to that 40 degrees, the velocity in the y direction is going to be the opposite side, making this 25 sine of 40. All right, so it says determine the time of flight, the horizontal distance, and the peak height of the football. All right, we're not told anything about where it's going to land, and so I'm going to assume that we're going to kick the football from the ground and it's going to land on the ground. Now remember, for displacement, we don't care the path that it takes. So the fact that it started here vertically and it lands here vertically, do you see they're at the same height? That means that my vertical displacement is going to be 0. So I'm going to have my initial velocity in the y direction. Now notice that that's directed up. So that's going to be 25 sine of 40 times t. I don't know t. So my initial velocity is directed up, but gravity is acting down. So I need to come over here and subtract 4.9. And I got that 4.9 by simply taking half times 9.8 times t squared. So if we move our 4.9 t squared over here, that's leaving me with 25 sine of 40 t. What's going to happen to one of the t's? One of the t's is going to cancel out, and in your math class they would have said, okay, one of the t values could have been 0, but that wouldn't make a whole lot of sense for us. So let's solve this. And so I get a time that this football is going to be in the air for a time of 3.28 seconds. So now I can come over here and find the range of my football by using the initial velocity in the x direction. Now remember, I've got to just use the component that's in the x direction, so it's not simply going to be 25, but it's 25 cosine of 40, and then times our time, which was 3.28 seconds. So the range of this football is going to be 62.8 meters. So that's going to be the horizontal distance that our football travels. Now the last part, it says find the maximum peak, or the peak height of the football. So we're going to find the peak height of the football. And remember up here that at the very highest point, my velocity is not 0, but my velocity in the y direction is 0. My velocity is going to be whatever the x component was, whatever the initial component in the x direction. So it's still going to be moving horizontally. It just stops briefly in the y direction. So to find that, I'm going to use another kinematic equation, and we've got our final velocity squared equals my initial velocity squared plus 2g delta x. So let's modify this for just what's happening vertically. So I'm going to say that's the final velocity in the y direction squared equals my initial velocity in the y direction squared minus, and I'm going to make it minus because gravity is acting down, 2 times 9.8. Now be careful with this. This is not 4.9. We use 4.9 a lot because a lot of times we're using the 1/2 at squared. This is actually going to be 2 times 9.8. Now instead of calling it delta x, let's call it delta y max. Now when you're finding the maximum height, this value is always going to be 0. So we have 0 equals my initial velocity in the y direction. It's not 25, but it's 25 sine of 40 squared minus 19.6 delta y max, and we can solve for delta y max. And we're going to get 13.2 meters. So this 13.2 meters is going to be the maximum height at this midpoint right here. Now this works for any time you're finding maximum height. What you could do in this case is we could have just taken our time, cut it in half, and then thrown it back in here. But that only works when the starting and ending position is at the same height. All right, so let's do another example. Okay, in this example, we have a student is standing at the edge of a cliff and throws a stone at an angle of 35 degrees. So our student is here on the edge of a cliff, and they're going to throw it with a velocity of 18 meters per second. So that's going to be my initial velocity is 18 meters per second. And it's going to be an angle of 35 degrees. That means I have a horizontal component of the velocity and I have a vertical component of the velocity. And you're going to absolutely have to break them into their components. Since my horizontal component is adjacent, that's going to make this 18 cosine of 35. Meaning my initial velocity in the x direction equals 14.7 meters per second. And I need to do that with the y direction as well. My initial velocity in the y direction is going to be the opposite side. So that's going to be the sine function. So I'm going to take 18 sine of 35, 10.3 meters per second. So that's 10.3 meters per second. As soon as you see the velocity is at an angle, you might as well go ahead and break up the components because we're going to have to focus on just horizontal and vertical. All right, and it says the stone lands 50 meters horizontally. So that is going to be a horizontal distance. And that horizontal distance has a very specific name and label, and that's called the range. And the range is going to be 50 meters. If I'd given you a vertical displacement, that would have been delta y. How long after being released does the stone strike the beach? I would just go ahead and start with write out horizontal and vertical. We're going to have to use both at some point. So we have horizontal and vertical. I've got my range equals my initial velocity in the x direction times time. And I've got delta y equals my initial velocity in the y direction times time plus 1/2 gt squared. Again, this is exactly what we did with the horizontal. The only difference is this term stays. All right, we have the range. I have the initial velocity in the x direction. I can go right to my horizontal question to find the time. So I've got my range is 50 meters. My initial velocity is 14.7, that's in the x direction. Notice I'm not putting in the 18. I solve for the time, and that gives me 3.4 seconds. How long after being released does the stone strike the beach? We found that. All right, over here we have delta y. Find the height of the cliff. Delta y is what we're looking for. My initial velocity in the y direction. Do I put 18 in there? No, I want just the component of the velocity that's vertical. Now this is directed up, and so since it's up, I'm going to make that a positive 10.3, and my time is 3.4 seconds. Now, the velocity was initially up. Which way does gravity act? Gravity acts down, and the way we reflect that mathematically is by the negative sign, and 1/2 times 9.8 is 4.9. And my time is 3.4 squared. So let's calculate this. And I get a value for delta y of negative 21.6 meters. And you may ask yourself, why is the height of the cliff, why is it coming up negative? And the reason for that is because look at where the projectile started. It started up here and it's ending below. And we said anything that ends below or ends directed down is going to be negative. Now, if I was going to write what the height was, I wouldn't say it's negative 21.6 meters. I would just simply say it's 26 or 21.6 meters high. And we'll see you next time.